Good morning everybody and welcome to Madrid, even if for most of us it's only virtually. My name is Patrick Boddy and I'm the Optronics Product Line Manager for Tecnobit, a Spanish company dedicated to the defence market with work centres in Madrid and Valdepeñas, a town normally better known for its wine, but I hope after this for its optics too. My talk today will be the right waveband, matching the technology to the application. I hope you will enjoy it. If I may, I think I'll start with a brief potted history of the company to let you know where we're coming from, and I guess to justify why we can talk with a certain authority on the subject. Although the company was founded more than 40 years ago, our involvement in optronics started in 1993 when we joined the Eurofirst consortium to develop the Eurofighter Pirate system. Rather amusingly, I was contracted initially for just 3 months to teach them all I knew about optronics and IRST systems. I sometimes joke that I must be a very bad teacher if I'm still here now. But the truth is, I like the company, they like me, and we've had a hell of a time developing some great technology together since then. Those first few years were a steep learning curve for all of us, so it wasn't until the year 2000 that we took our next steps in the optronics market. That year we were awarded contracts to build to print the Rafael Lightning laser designation pods for the Spanish Air Force, as well as parallel contracts to develop new thermal cameras, a higher resolution medium wave for the Lightning and a replacement long wave camera for the Spanish Air Force Nighthawks that were suffering terrible reliability problems at that time. Little did we know it at that time, but it turned out we were almost the first in Europe to develop a 640 resolution FPA medium wave camera, and the long wave camera too was quite novel, integrating as we did both CMT and QUIP detectors. From these humble beginnings, we decided we should include complete systems in our portfolio, and so we developed 2 new multi-sensor systems. The first to be finished at the beginning of the year was the Centinela, a pan and tilt for ground surveillance applications with a GPS and digital mapping system, which was delivered to the Spanish Marines. And a few months later, towards the end of 2007, the Argos, a 4-axis gyrostabilized system for the Spanish Navy. – 2012 was a pivotal year for optronics and Tecnobit with 2 very important programs. The first was a contract for the delivery of our cameras to Rafael in Israel for their systems in the United States. We are especially proud of this achievement since, and I'm sure many of you will agree, a Spanish company selling thermal cameras to an Israeli company is like selling snow to Eskimos. The second, possibly even more important program involved the development of new medium wave and long wave cameras packaged within a pan and tilt system for a Middle Eastern country, along with extensive transfer of technology, including on-the-job training. We like to think that 2012 was the year we went from being apprentices in optronics to becoming full masters. The next technological jump was the award in 2014 of the FITE contract. Previous to this, our principal involvement in the Pirate IRST was standard video image processing, gain and offset correction, histogram equalization, edge enhancement, graphics, etc. etc. Although obviously we had a good understanding of how the whole system works. In the FITE program, we began developing our own complete suite of software and firmware algorithms, which include automatic detection, tracking and classification of multiple targets, giving us complete autonomy over the system and establishing us truly as an IRST company. In 2015, we began the upgrade of our existing cameras and systems with the addition of HD resolution thermal cameras, digital video outputs, and improved stabilization, as well as a host of other improvements to increase reliability and shorten maintenance tasks. In another major milestone, based on our background in the Pirate IRST and the success of the FITE trials, in 2016 we were awarded, jointly with Indra, the development contract for the new naval IRST for the future Spanish F-110 frigates. Our first success in the remote weapons sight market came in 2017 with 2 major programs. The first was the award of a contract from Saab for a new sensor module for their truck-fire weapon using medium-wave cameras. The second was an agreement with Rafael to develop a new super compact continuous zoom medium-wave camera to be integrated into their systems. More success was to follow in 2019 when we became the preferred supplier for daylight and thermal cameras to one of the top air defence companies in the world. This after they finished extensive comparative testing between our cameras and those of 5 other major European suppliers. And finally, this year we were awarded, with Indra, the production contract for the naval IRST system for the Spanish Navy F-110 frigates. In summary, in the last 28 years we have gone from learning basic video processing for thermal cameras through to developing our own cameras in several wavebands with complex stabilised systems which we include into the most state-of-the-art complete IRST systems. Here we have the classic wavelength atmospheric transmission diagram, divided into the separate wavebands we are all familiar with. The enormous civil market for visible cameras means the sensors and optics are relatively low cost and available with very high resolutions. However, it is also the band most affected by haze and fog, and so it can have limited range under many atmospheric conditions. The near band loses the advantage of colour but gains in range, being able to see through mist and haze that would otherwise block the visible. Fortunately, it uses the same silicon CMOS sensors as the visible, and many COTS optics are also designed for near. This allows developers, such as Technobit, to integrate a near mode into their visible cameras to provide a dual band camera. The SWIR band extends the ability to see through mist and smoke, but one of its main uses in defence systems is as the ultimate long-distance camera. This is because its short wavelength allows the camera to be far more compact than an equivalent range thermal camera, while still having excellent transmission through the atmosphere. Its ability to see lasers used in defence applications in the 1 to 1.7 micron waveband is also a big advantage. The sensors are normally in-gas, which are uncooled, though they are still relatively expensive and low resolution. SWIR optics can be the same optical materials as the visible, but very few commercially available optics are suitable for SWIR in defence applications. The medium wave band is the shortest wavelength thermal band, and almost all detectors in this band need to be cryogenically cooled. Some materials, such as indium antimony, still need to be cooled to 77 Kelvin, but hot detectors are fast becoming the norm, with mercury cadmium telluride now operating above 120 Kelvin and indium aluminium antimony at 150. Between 70 to 80% of thermal cameras being developed currently are medium wave, with an ample range of COTS optics available. We'll talk of why that is next. The long wave band was the first thermal band to be used, and although originally all cooled, is now dominated by the uncooled microbolometer sensors, used from night driving aids in high-end cars to sites on remote weapon stations. The use of cooled long wave is now much more of a niche market, which we will cover presently. In these next few slides, I'd like us to look at the relative pros and cons of the two thermal bands. As we all know, the amount of energy radiated from any object depends on its temperature, and if we assume black body behaviour for now, the relationship follows Planck's law, as shown below. The first observation is that at these temperatures there is much more energy available in the long wave than the medium wave. As a matter of fact, the medium wave doesn't overtake the long wave until about 500 Kelvin. This is of course why uncooled microbolometers are able to achieve such good results without the need for expensive, heavy and limited life cooling engines. Since the medium wave detectors are generally more sensitive than even the cooled long wave detectors, and medium wave often suffers from less atmospheric transmission losses, at normal ambient temperatures the sensitivity of medium wave and cooled long wave cameras are broadly similar. However, once we step outside this normal ambient temperature, we start to see some significant differences. For instance, whilst the additional sensitivity of the medium wave can compensate for a difference in radiated energy by a factor of 8 for objects at 25 degrees centigrade, by the time we reach 0 degrees centigrade, the ratio is now 12.7. And at minus 20 degrees centigrade, the medium wave camera is receiving almost 1/30th of the energy of the long wave camera. On the other hand, the ratio in the long wave between the energy radiated at 0 degrees centigrade and 100 degrees centigrade is a mere 5.5. For the medium wave, it is greater than 4 times more, a ratio of 24.1. This behaviour has two simple consequences. First of all, the medium wave will struggle at very low temperatures. This can be mitigated by longer integration times, but then the second problem kicks in. The dynamic temperature range of a medium wave detector at any one particular integration time is less than that of the long wave, with the result that in scenes with very cold backgrounds and very hot objects, we either get saturated objects or low scene contrast. This second problem is sometimes known as blooming, and although it can be mitigated via various techniques such as double integration times, it is something to consider in weapon systems such as missile launchers. Until recently, one of the disadvantages of the long wave band was the reduced resolution of the FPA detectors. They turned out to be far more difficult to manufacture than their medium wave equivalents, although the situation has now improved. Both XGA and HD format cooled long wave detectors are now available. Although we are not aware of any full HD cooled long wave detectors yet, and even less so of the imminent arrival of 5 megapixel devices, as is about to occur in the medium wave market. Cooled long wave detectors still also have no equivalent to the hot medium wave either, with MCT, Type 2 superlattice and QUIP all requiring 77 Kelvin or below. The difficulties of manufacture, the lower volumes and the more expensive coolers all combine to drive the cost of cooled long wave detectors to be a lot more expensive than their medium wave equivalents. Interestingly enough, full HD 12 micron pitch uncooled long wave detectors are available, which probably says a lot about where the market is heading. The law of diffraction means quite simply that the smaller the wavelength, the smaller your optics can be. The relative size of the Airy disk with respect to the detector pixel size is a subjective value and one that also depends on the type of application. There is no doubt that the low F number produces a sharper, crisper image, but I have always stuck to the advice I was given in one of the first spy conferences I attended. A speaker from the US Night Division Directorate told me that to get the maximum range from your camera, the optical MTF should not drop below 20% before the Nyquist sampling frequency of the detector. In other words, the Airy disk should be no larger than 3.5 times the pixel pitch. And I'm glad to report that our experience in Technomate is that this is true. We've tried a 4.2 ratio once and it really didn't work out. Anyway, the long and the short of it means that to achieve the same DRI ranges, a cooled long wave camera will require optics twice the size of a medium wave camera, and even larger for an uncooled long wave camera, partly due to sensitivity, but also due to working at up to 14 micron. It's worth mentioning too that the lightest and cheapest material for thermal camera lenses is silicon, and this does not transmit in the long wave band. And so, as well as being large, the long wave lenses are also heavier. The difference in weight given here between our new compact medium wave camera and a potential uncooled long wave camera based on a COTS lens assembly is a good example of what can be achieved. Smaller, lighter, cheaper. All this helps to explain why medium wave cameras dominate the medium to long range markets. The atmospheric attenuation depends on the temperature, relative humidity and a host of other aerosols. As you would expect, the worst transmission is close to the Earth's surface, but starts improving above 200 meters. I've already mentioned how the visible can be badly affected by haze, and here you see a classic example of the advantages of near that maybe some of you have seen before. The longer wavelengths are not scattered in the same way, but suffer more from absorption. In some trials I carried out on the coast of Spain a few years ago, the morning sea fog prevented both the visible and long wave to see an oil tanker at just 6 kilometers, but the medium wave was able to see right through to the cars on the Moroccan highway, 35 kilometers away. In colder, drier conditions, the long wave might have been the better choice, but as a rule, for surface applications, and especially naval, I consider that the medium wave has almost always better transmission. An interesting point is how the long wave and medium wave attenuate according to the Stanag 43-47 rule. As you would expect, since almost all systems were long wave when the Stanag was published, its attenuation factor closely matches the Modtran analysis. Medium wave, however, does not, showing a much steeper attenuation to start with, followed by a better transmission after 10 kilometers. Another observation is that the blue medium wave suffers less attenuation than the red medium wave. Here is another diagram of the transmission, showing the details of how the red and the blue bands are attenuated. This is especially interesting since this compensates for the reduced sensitivity due to the low energy levels of the blue band camera when tested in laboratory. Now that we've covered a few of the principal features of the technology, I'd like to discuss some case studies for airborne, ground mobile and naval applications based on programs we are working on and some that we are hoping to work on. And since optronics were founded on the Pirate IRST system, I thought we'd start with this application. IRST systems are designed to be part of the primary sensor of any modern fighter and to provide a function similar to the radar, but in a totally passive manner. Whilst using a radar immediately alerts the other aircraft to your presence, the IRST emits no signal, and even if the opponent is aware of the aircraft fitted with the IRST, there is no way to know if the IRST is tracking him. While there are techniques to reduce the thermal signature of aircraft, it's not easy. Most existing systems are forward-looking, for the same reason that the radars are, but also due to limitations of budget and to the existing technology at the time they were developed. However, air forces are increasingly interested in omnidirectional systems for the frontline aircraft like that of the F-35 that can detect threats and targets from any direction. Although, combining the range of forward-looking systems with the coverage of an omnidirectional system will come with quite a heavy price tag. An important point is to make that even the longest range IRSTs are not designed for visual identification of targets at long ranges. This is normally achieved with other optronic sensors. So, what are the main requirements of airborne IRST systems? Well, first of all, very high spatial resolution. It needs to cover a very wide area with a very narrow instantaneous field of view. Everything, of course, depends on the required ranges, but to come close to the performance of the Pirate would require significantly more than 300 million pixels for an omnidirectional system. Even then, the system relies on subpixel detection. A low F number is required and very sophisticated algorithms. Here we can forget about the Stanag 43-47 requirement of 1.5 pixels over the critical target dimensions. At least for now, optical scanning will be required to provide the required instantaneous field of view with the detectors that exist or will exist in the foreseeable future. In order not to miss any event and to detect in the shortest possible time, very fast scanning must be used, preferably faster than 1 Hz. And all of this will of course require quite some processing power. So, let's see what the ideal solution for an air-to-air IRST system is. The sources of radiated energy from the aircraft come principally from the engine and the heating effect of the air friction on the skin. While the temperature of the engines leads itself to better detection ranges in the medium wave, and many air-to-air missiles use the medium wave band for precisely this reason, once viewing an aircraft from other angles, the primary radiation source is the aircraft's skin that emits far more in the long wave band as shown in the diagram below. Indeed, the comparison given here is for supersonic aircraft with significant heating. Since the heat generated is a function of the square of the Mach number, In the case of subsonic aircraft, there is far less heating, and whilst this will affect both bands, it will affect the medium wave far more due to the already very low temperatures. If we remember, at minus 20 degrees centigrade, the energy in medium wave is 30 times less than that of long wave, and even lower temperatures are common at high altitude. So even when considering only the sensitivity, it is clear that long wave technology seems the better choice. But its wider dynamic range is also an advantage when scanning over a wide area which may include quite different temperature profiles. And the shorter integration times allow for faster stop and stare scanning, which is essential if we are to achieve a high field of regard frame rate. With relatively wide fields of view, the size of the optics is not an issue for IRST systems, and the apparent lack of very high resolution detectors and relatively costly detectors is probably a problem that is perfectly solvable with a big enough new aircraft program. One should never underestimate the effect of budgets on the final solution, but technologically the choice is quite clear. Electro-optic targeting systems, or laser designation pods as we used to call them, are primarily conceived for air-to-ground attack. Here we are not searching a large area for possible threats, but rather providing close air support to ground forces or targeting known locations. The objective is therefore to be able to identify visually with the greatest possible detail the targets prior to engaging them with laser-guided weapons, whilst remaining, of course, at a sufficiently safe distance. This drives the solution towards medium-wave thermal cameras with high F numbers that can offer twice the range performance of comparable long-wave cameras of the same size and weight. Whilst ground targets can be at very low temperatures, they are not comparable to the air-to-air situation, and their narrower fields of view and the longer integration times compensate for any loss of sensitivity. Indeed, the drive now is for even longer ranges whilst reducing size and weight, which implies a common aperture optics design. This is normally a single catadioptic lens, such as the example of the Reaper MTS-B shown below, with beam splitters to split the various wavebands and feed them to the medium wave, SWIR, near and visible sensors mounted behind, allowing much longer focal lengths whilst maintaining a multiband system. In all cases, the very narrow fields of view require high levels of line of sight stability, low latency for accurate tracking, and very good alignment between the cameras and the laser designator. It is important, after all, that the laser is illuminating the right target. Our solution to this last requirement was to include a C-spot function in the medium wave camera so that it can see the laser designator and so be 100% sure that the thermal camera and the laser are perfectly aligned. Modern armoured vehicles typically can have a large number of optronic sensors. As a minimum, they will have sights for the weapon systems, from simple, low-cost, long-wave-based sights for the smaller caliber weapons to longer-range pairs of sights for the larger caliber weapons, with 360-degree viewing for the commander to allow them to operate together in a hunter-killer mode. Driver night vision cameras are also becoming almost obligatory, as are 360-degree situational awareness systems, though these are often still visible only. And lastly, mast-mounted long-range cameras for forward observers, or just for longer distance situational awareness, are proliferating. Each system has very different requirements, and the choice of sensor thus varies considerably. But all optronic systems have one thing in common. Armoured vehicles are manufactured in far larger numbers than ships and aircraft, meaning the optronic solutions, or for that matter, any other equipment, are far more price sensitive. With their wide fields of view, short ranges and limited budgets, uncooled long wave is the obvious solution for driver nighttime vision systems. To contain costs, most systems use VGA resolution, which limits the field of view or the range, but the new 12-micron HD detectors, which are now available and are only marginally more expensive, will provide a step change in the image quality. The best systems should include visible and image fusion to see the maximum information possible, and Technomit's long-wave engines are designed with an interface to HD CMOS sensors. While the driver night vision system only provides an image to the driver, the LSAS system automatically detects targets and threats just like an IRST system, as well as providing video of various formats to several points in the vehicle, such as the commander, the gunner, or the infantry squad being transported. Like the driver night vision system, the most cost-effective solution is an uncooled long-wave camera in combination with an optional visible band camera, with the overall system consisting of several of these cameras around several points in the vehicle in a DAS architecture. Just like the night vision, the ideal solution, now that the 12-micron HD detectors are available, is to reduce the total number of sensors through their use, although in some cases a mixed resolution solution may be more appropriate. An HD sensor may not be needed, for instance, for the reversing camera or for when observing right up against the wheel. Technomit is currently studying the possible development of a situational awareness system baptized ARES, based on elements it has developed for its IRST program. For small caliber weapons below 12.7mm, where the range is relatively short and the need for an economic solution critical, the choice of sight is quite simple. A 1 or 2 field of view uncooled long-wave camera with a visible band camera and a low-cost laser rangefinder. Larger caliber weapons have traditionally favoured cooled long-wave to achieve longer ranges than the uncooled with no blooming during firing. However, these are significantly more expensive than the equivalent medium-wave cameras that are also much smaller and lighter. This may be less of a problem for new main battle tanks, but especially for remote weapon applications and armoured vehicle upgrades where budgets are tighter, more and more systems are turning to medium wave to achieve both longer recognition ranges, which is essential for positive identification, and to meet their objective costs. To overcome the blooming problem, Technobit have implemented algorithms that are able to limit the time that the camera is saturated to an acceptable level for the gunner, and these are now in service on the Saab Trackfire with excellent results. Although the Trackfire is a 12.7mm caliber weapon that principally chose to use the medium-wave camera to improve ranges in maritime environments, most 12.7mm systems still use uncooled long-wave cameras due to their price, reliability, and almost instant availability. However, this equation may be about to change. The use of hot medium-wave detectors operating at 150 Kelvin or above is starting to become more common, which reduces the cool-down time and increases the life of the cooler. With a cool-down time of just 90 seconds, Technomit's new camera is operational in little more time than an equivalent uncooled long-wave, while providing at least 2 or 3 times the range. Moreover, the 30,000-hour lifetime of the cooler means that many users will never need to renew it during the service life of the weapon system. The reduced size of the lenses, the extensive use of silicon, and a revolutionary new detector also means that the camera is not significantly more expensive than the equivalent performance uncooled long-wave, and this should open up a market for medium-wave cameras in 12.7mm and possibly even smaller. The forward observer is responsible for directing artillery and mortar fire onto a target, and may be a forward air controller for close air support. For this application, very long-range cameras are required to maintain distance between the opposing forces, which implies, of course, a medium-wave camera. They also need excellent boresight retention and low latency for accurate tracking. High-definition video is preferred not only to provide superior image quality, but to maintain context, and the use of 10-micron pitch or less detectors allows the right cost-performance balance. Indeed, the use of XGA detectors can be a useful compromise to provide a jump in image quality at a more economical price than the true HD alternative. As part of the close air support function, many systems such as the Spanish 8x8 also provide laser target designation, in which case the correct alignment between the designator and the camera is a must. Since the laser designator wavelength is outside the waveband of the visible sensors, this is normally done by an additional sensor, but can be done by the medium wave camera if designed correctly, as has been done for the Spanish 8x8 observer. IRST systems on ships were uncommon until relatively recently, and even the navies that did have them tended to have just a few. Unlike airborne systems, which have typically been forward-looking, as a relatively slow-moving platform with threats and targets liable to appear from any direction, 360-degree coverage around the ship was required from the start. Due to the variability in climatical conditions and the high value of modern warships, dual-band thermal are preferred. Many of the installations, and especially the older legacy systems, use rotating cameras, typically with a 1 Hz revolution, either mounted on a stabilized system to compensate for ship pitch and roll, or with this mechanism built into the camera head. These are more than adequate for detection of other surface vessels and typical asymmetrical threats such as from jet skis or RIBs. However, the threat that keeps admirals up at night are long-range sea-skimming missiles. These are difficult to detect with radar sensors, and in the case of a supersonic missile, it can reach the horizon to the ship in less than 30 seconds. The horizon is only 16 kilometers away after all. Considering that the time to act on the information is so short, and that to classify a threat with the required false alarm rate requires several consecutive detections and an accurate calculation of heading, no system can afford to waste several seconds before issuing a warning. The importance of a much higher refresh rate than 1 Hz then becomes very evident. As explained in a previous slide, in most naval situations other than Arctic conditions, the medium wave suffers less from absorption losses than the long wave band, and so has a longer range. In addition, the air temperature is far warmer at sea level, and even subsonic aircraft or missiles produce enough radiated energy from their forward surfaces to be detected while heading directly towards the ship. For this reason, the primary long-distance sensor of naval IRSTs are generally medium wave, and this is also true of Technobit's naval IRST, which includes a number of high frame rate staring cameras. Nonetheless, the Technobit solution also includes shorter range long wave cameras as a backup, which together with some visual cameras have a wider vertical field of view to better cover short range threats in ports and in coastal situations. The complete IRST system is made up of 4 fixed sensor modules mounted into the integrated mast, each covering a sector of just over 90 degrees. They have no external moving components and each includes all 3 types of cameras. The central processing unit, in which all the detection, tracking and image processing is done, is mounted in another part of the ship remote from the sensor modules. Like the airborne systems, the IRST prime function is to detect, track and classify targets and threats, but not to be able to visually identify at long distances. The system therefore includes 2 separate gyrostabilized turrets for this function, one on each side, which is slave to the position of any high-level threat or target for positive identification with its very narrow field of view, medium wave and visible cameras. As can be seen from the image, in naval applications, size and weight are not such an issue as they are in aircraft. That concludes my discussion of the characteristics of the different optronic sensors available in the defence market and my view on the correct selection according to the application. I hope you enjoyed the talk. I'll just end with what I see as the essential strategy for success in the development of optronic systems in our market. First and foremost, keep up with the detector technology. You have to be ahead of the game. Not always possible, but having your own optomechanical designs achieves better control of quality and cost and avoids product obsolescence. For electronics, where component obsolescence is always a threat, mitigate by developing new, backward compatible, more compact and more powerful designs. Develop the complete product. Although we are principally a Tier 2 company supplying cameras to others, the development of a complete gyrostabilized system allows us to fully understand the needs of our customers. We cover all wave bands, visible, near, SWIR, medium wave and long wave. Sophisticated image processing algorithms are just as important as great optics. And last of all, never underestimate how much processing power you need for an IRST product. And here, a small sample of our satisfied customers. Thank you very much, and I look forward to your questions.